looking at number 9, it says in the book, in this exercise, you will discover whether knowing the x-intercepts determines a unique quadratic equation. What do you guys think that means? So, in this sentence here, discover whether knowing the x-intercepts determines a unique quadratic equation. What do you think, Emily?
It means, like, can you only make one equation from a set of x-intercepts?
Yes. So, raise your hand if you understand that. Can you only make one equation from a set of x-intercepts is what the question is. Okay, so we're going to do that investigation by figuring that out. So it says write an equation of the parabola of x-intercepts of 3 and 7. Okay, so you have 3 different kinds of equations you know about. You know about vertex form equation, general form equation, and factored form equation. Given that you have roots, x is equal to 3, x is equal to 7, what equation do you think is going to be best? You can use any one, but what one's going to be best? Factored. And actually, can you even do vertex?
No.
What do you need to do the vertex equation? The vertex, which we don't have. We have the roots. So let's go ahead and use factored. So I had said earlier to someone, you don't need to make any equation. It's just the bare minimum equation that you can. So given these roots, what would be the equation? Y equals, do you need an A? No. Okay, y equals?
X minus 3 times x minus 7.
Perfect. Okay, so that's our equation for A. Okay, it says name the vertex of the parabola in 9A. So you are going to need a graphing calculator, and I'm going to clear it. So you're going to plug in to y equals your equation of x minus 3 times x minus 7, and you are going to have to graph this to find the vertex. Now, the vertex is going to be the lowest point, and I'm looking at this and I'm counting, I'm just going to estimate when x is 1, 2, 3, 4, 5. It looks like approximately when x is 5, and then approximately when y is like either negative 3 or negative 4. The way you figure this out is you go on the table. So I'm going to go to the table and find when x is 5. And if you check out this, when x is 5, it's negative 4, but do you see how it goes? 5, 0, negative 3, negative 4, negative 3, 0, 5. So it's like doing this. It's like dropping and then going back up, right? So negative 4 is our lowest point, so it's 5, negative 4. So I'm going to say for my vertex, it's 5, negative 4, okay? So that's B. C says modify your equations in 9A so that the graph is reflected across the x-axis. Okay, here's my equation. Now, just for logistics, I'm going to show you guys. You probably want to change this to general form, okay? So I'm going to say x times x, x squared, negative 7 times x, negative 7x, negative 3 times x, negative 3x, and negative 3 times negative 7 is positive 21. So our equation is also y equals x squared minus 7x, I'll say minus 10x, plus 21. The reason I'm having you change this is because it's hard to reflect a graph that has factored form. You can still do it, but it's hard. When you reflect over the x-axis, what's happening? What's changing to its opposite?
Y.
Y. So if that's the case, you have to do what to y? So y becomes negative. You have negative y equals x squared minus 10x plus 21. When y is negative, you can't graph it, so you have to divide by negative 1, divide by negative 1, and then you end up getting y equals negative 1 divided into x squared is negative x squared, negative 1 divided into negative 10 is positive 10x, and then it becomes negative 21. Does that make sense?
Mm-hmm.
Question?
Can't you just like look at the graph and
You could, yeah.
wouldn't that be easier than changing to general form?
Well, it says modify your equation so the graph is reflected. So I just
okay.
modified my equation.
Okay.
So now I'm going to graph that equation here, and I'm going to say negative x squared plus 10x minus 21, and I'm going to graph it. Okay, so my original is on top. What's happened to my roots of 3 and 7? Do you know?
Wouldn't it also work to just do the same equation but put negative in front of it? Because I got the same graph.
Okay, so if you were to write it just like this, is what you're saying? Like, if you had y equals negative and then x squared minus 10x plus 21?
No.
No, like
Negative
negative x minus 3 times x minus
Okay,
7.
the only way that would work is if you had y equals x minus 3 times x minus 7. If you put an entire parentheses around this and then put a negative out here.
I thought I got the same
Yeah.
line.
The graphing calculator might be doing that, but do you understand that if you put a negative just out in front of here, it might not work, depending on how you graph it.
So
Yeah.
can we do that?
If you know that it's supposed to reflect and it doesn't reflect, you need to adjust your equation. Does that make sense?
Yeah.
So yes, as long as it's actually showing up as this on the graph, that's fine.
Okay.
Okay. So here's the question though. Our first one was, do we know if x-intercepts determines a unique quadratic equation? So does this mean that the roots of 3 and 7 can only happen in one equation? Can you verbalize what you're doing with your heads? You're doing this?
No.
Okay, so 3 and 7 are the roots of this equation, right? They're the roots of also this equation, right? Does that make sense? Okay? It's now asking, what if we stretched it? So I'm going to write my original equation here. Y equals x minus 3 times x minus 7. How do I stretch something vertically? Vertical is what letter? Okay, stretching is A, but what side deals with vertical? X or Y? Y. So if I'm going to stretch something vertically, what do I need to do to Y?
Well, never mind.
So, yes, if you want to stretch something, you're dividing. Remember how it's opposite? So I'm going to divide y by 2. Okay, if that's the case, how do I get it on the other side so I can work through this? Multiply. So I'm going to multiply both sides by 2, multiply this side by 2. I now have y equals 2, and then x minus 3 times x minus 7. I'm going to go ahead and I'm going to graph that on my y2. So I'm going to say 2x minus 3 times x minus 7 like this, and I'm going to graph. There's my original equation there, and then that's my new equation. Are the roots the same?
Yeah.
Okay. Is the vertex the same?
No.
It's in the same x spot, right? Which is 5. Let's go to the table. When I have my x is 5, my original equation has negative 4. My new equation has negative 8. Right? But the question is, can the roots work for more than one equation? These roots. So far, this equation it works, this equation it works, and this equation it works. So here's the final answer, or final question. How many quadratic equations do you think there could be with x-intercepts at x is 3 and x is 7? Okay, since none of you are answering, I want you to talk to your tables about this. Answer the question with your tables. How many x-intercepts, or how many graphs could there be?
Yeah.
Well, there are. Yeah. I mean,
What would have had to be? Yeah.
one you can still do.
Okay, bring it back. 5, 4, 3, 2, 1. Who has an answer? Yeah.
There could be infinite because there's an infinite number of dilations you could do, and then you could reflect it over the x-axis.
Okay. So I'm going to revoice what Emily's saying. You could stretch it. How far could you stretch it before the roots would not be the same? Forever. How much could you shrink it? And then you could flip it and do the same thing, right? So the whole point here is the roots given are not unique to one equation. Show me on your thumbs. Does that make sense? Okay, awesome. Thank you. Does it